Hello and welcome. This is our ISQED special session paper presentation regarding hardware-software co-design for approximate in-memory computing. My name is von-Neumann and my co-authors are Hong Nguyen and Hussam Amrouch. In the last 20 years, the interest in performance of machine learning has been skyrocketing. One of the decisive factors were the datasets that got more and more elaborated and grew in size. One of the more famous one is ImageNet with 1.2 million images. On it, an annual competition got hosted by the name of ILS VRC. Through this competition, researchers figured out that it is actually beneficial to add more and more layers to their neural networks. Now we have neural networks, deep neural networks, that have well over 100 layers with millions and millions of weights. This combined needs a lot of space on the disk, and it is this combination that blatantly exposed a fundamental flaw in our computer architecture. Here we can see a simplified sketch of our computer architecture, where we have on one side the compute units and on the other side the memory blocks connected via bus. And it is this bus that needs to transport all the data to and from these blocks. But this bus is very restricting, and it therefore got its famous name of the von-Neumann bottleneck. And not only does this bottleneck introduce a lot of latency during the transportation, but it is also very heavy in energy. Now the question might be, how can we resolve this issue? And one idea might be very simple, that we can try to completely eliminate this transportation by simply combining these two things together, and we call this in-memory computing. So we enhance the memory blocks that they are now capable of performing computational operations. When we take a look at literature, we can see that many different technologies can be used to implement such in-memory compute schemes. For example, conventional CMOS technology, or emerging technologies such as ferroelectric transistors, phase change memory, memristors, or spin transfer torque devices. But in-memory computing is also not the silver bullet as we make it out for. Its inherent analog nature and also the unreliability of the emerging technologies contribute to the errors, to randomness, simply to approximation in these in-memory computing schemes. But it is these errors, this approximation, this randomness that harms the application that we try to run on this hardware. And in our case, we wanted to run machine learning or deep neural networks, but they are not able to deal with this randomness, with these errors. So through this randomness and the errors, for example, the inference accuracy drops really dramatically. Okay, so we cannot use the state-of-the-art algorithms. What do we have to do? Well, we have to come up with new algorithms, and this is where hyperdimensional computing comes in. It is a brain-inspired computational algebra and is actually based on randomness. This means that it is actually inherently resilient to errors because of its foundation on randomness, and it uses patterns rather than specific values that decode specific information. Another feature of hyperdimensional computing is its data efficiency. It is capable of abstracting from very little data. We now want to take a look at the language classification example with HDC and how an algorithm might look like. So we have the training text, and we run these real-world objects, in our case the text, through an encoder. And this encoder is capable of taking these real-world objects and transforming them into a hyperdimensional vector. Now we do this for every language that we want to learn, and each resulting vector we then store in a so-called associative memory, and these are our class hypervectors. What we then do when we want to query text, we take this piece of text and we pass it through the very same encoder, and we again get a hyperdimensional vector, which is our query vector. What we then have to do is we have to compare this query vector with all the class hypervectors in our associative memory, and we want to find the closest class hypervector to our query vector, and the language that is associated with this class vector is then the language that we infer at the end. Now the question is, okay, what means closest in our sense? When we, for example, implement our hyperdimensional vectors with binary vectors, then the closest vectors is decided by the Hamming distance. So the question is, we have to calculate the Hamming distance of the query vector with all the class hypervectors in a very efficient way in the associative memory, and this is where our research is located. Now we want to take a look how we actually implement our in-memory computing scheme, and for this we use so-called TCAM cells. Now on an abstract level, a TCAM cell is able of storing a single bit information, and we can then query this cell with outside data. When we query it with data, it will compare the query data with the internal stored value, and if they are the same, the cell will respond with a match or a logic 1. When the query data and the internally stored value do not match or are not the same, it will respond with a mismatch or a logic 0. Now let's take a look how we can implement that with conventional CMOS technology. So here we use at the core 2 SRAM cells to store the internal state. And then we can see on the left and right hand side of the cell where we apply the query data, which is through SL and SL bar. And what we can further see is that we have the output of the TCAM cell, which is here the match line. And we can see that the match line is connected to ground through these two possible discharge paths over SL and SL bar respectively. Now, what will happen in the case of a match? There will be no conducting path from the match line to the ground, and because we have pre-charged the match line previously, it will stay high or logic 1. In the case of a mismatch, exactly one of the two paths will form a conducting path, and it will draw the matchline voltage down, and this is signalizing a mismatch. We can then go and take this TCAM cell and connect it via a shared matchline and build a TCAM array. And what we now want to do is take a look at a simple example where we want to store the bit string of 110, and we want to query it with the bit string of 101. We can also do this computation by hand, and we will find that the first cell will produce a match and the later two cells will produce a miss. Now, we just saw what a TCAM cell will do in case of a miss. It will form a conducting path from the matchline to the ground. So we now have these two cells that form two parallel paths from the matchline to ground and discharge the matchline. And it is this discharge current that we can then go and measure with a sense amplifier to find out how many of the TCAM cells are signalizing a mismatch. And when we now take a step back and try to look from an abstract way what we are just doing here, we actually find that we have just computed the Hamming distance of the stored bit string versus a queried bit string. And it is through the discharge rate that we can actually deduce the Hamming distance from the discharge rate through the sense amplifier. On this slide, we can see a sample output of the sense amplifier at different Hamming distances. So we can see on the far right side, this is the output signal for a Hamming distance of 1. And we can see that the output of the sense amplifier, the operation latency, gets faster and faster the higher the Hamming distance is, because we have more TCAM cells that form a conducting path. So the discharge rate is higher, and therefore the sense amplifier notices the discharge earlier. Now, to measure the operation latency, we simply cut at 10% VDD, and we can then read the operation latency for each individual Hamming distance. So what we are now interested in are several trade-offs regarding this particular implementation. And what first comes to mind is, for example, how can we make this implementation more energy efficient? And one observation that we always have with SRAM cells is they are very leaky. They consume a lot of leakage power because they, for the most of the time, sit around and just hold the values. So what we can do is we can go and split our supply voltage into two ways. So we have the overall voltage supply, and then we have one supply voltage that is dedicated only for the SRAM cells, and we call this VDD cell. Now the question is, okay, we have a computing scheme which is already approximate. When we now reduce, for example, the voltage for the SRAM cells, how will this impact our overall approximation, our error probability? And when we also bring process variation to the table. And this is what we've done here. So we have applied process variation onto these different voltage configurations, and we can actually see that in, for example, the first row, there are voltage configurations that completely break the circuit. This in particular happens when the overall voltage supply is far smaller than that of the cell. When we have working voltage configurations, we can see that we now have these nice histograms of distributions for our operation latency. And what you can also see here are these red bars, and these indicate the decision boundaries in between the heaps of Hamming distances, which we use to decide what operation latency we attribute this Hamming distance. And what we can also see for these two examples that we picked here, that by changing the voltage configuration, we can actually produce more margins between the decision boundaries, but we can also see that the spread of the operation latency distribution also increases. So the question is at the end, what is more beneficial and what is the optimal voltage configuration regarding the error probability? And for the error probability, we simply count the samples that spill over into the wrong bucket of the decision boundaries. So with this slide, we summarize our findings. And here we can see that the groups are nicely grouped by the overall supply voltage. And then only on a side factor, we have the voltage for the SRAM cells. This means also in return that we are actually possible to heavily scale the voltage for the SRAM cells down, and we don't have to pay too much in error probability, because it is more important to pick the overall supply voltage in a correct way when you want to minimize error probabilities. This we can also see in this graph. Here we now go to the actual application of hyperdimensional computing, where we compute the inference accuracy for the language classification example. And we can see here that we compute the inference accuracy loss. This means we compare our samples versus an ideal inference accuracy, which we computed without any errors, without any process variation. And we can see here again the same thing that we saw earlier. It is more important to pick the correct supply voltage, and then only as an afterthought we have to take a look at the voltage that we pick for the SRAM cells. Or again, we are actually able to drastically scale down the voltage for our SRAM cells and save leakage power. This concludes the conventional implementation. We now want to take a look at an emerging technology, being the ferroelectric transistor. Now the question might be, why do we want to take a look at it? So first of all, FeFET devices are non-volatile, which means there is no leakage power, so we can completely power gate our TCAM array and it will not lose its state. The second and also very interesting factor is its bit density. We can see here on the right hand side the full schematic of a TCAM cell based on ferroelectric transistors. We can see that we only need 2 transistors which are able to hold the state, and then we do the very same thing with the SL and SL bar to apply the query bit. This means when we compare it directly that we actually need 8 times less transistors. Here we only have 2 transistors, and the conventional CMOS implementation needed 16 transistors. But also not everything is golden with ferroelectrics, because we now implement a new ferroelectric layer into the transistor, which adds more sources of variation, and we are less reliable in the end. Also, the TCAM cell based on ferroelectrics performs worse in sense of operation latency than the conventional implementation. What we now want to take a look at are specific challenges with the ferroelectric transistor, which again are variation, and now we want to take a look at delay. So what we've done here is we've focused on a single ferroelectric TCAM cell, and we make it subject to an imaginary clock, meaning that this ferroelectric TCAM cell needs to pull down the match line fully below 10% VDD for it to produce a valid output. And if the imaginary clock comes earlier and the match line voltage is still too high, then it is considered wrong. Naturally, we can see that in the very beginning, the error probability is 100%, because not even the best TCAM cell is able to pull down the match line voltage fast enough. But what we can then see is when we make this circuit subject to different configurations of the match line voltage, that it is actually beneficial to apply less voltage to the match line, because it produces less spread at the end, which means that the reliability with less match line voltage is better versus the higher match line voltage configurations. This brings me to my summary. So we saw that in-memory computing is inherently approximate, and this kills the classical machine learning applications as algorithms to run on this approximate hardware. So this is the reason why we have to look into emerging algorithms, being it hyperdimensional computing or something else. And lastly, we've seen that hardware-software co-design is a key to make a bridge between our approximate hardware, being in-memory computing, and our software side, being these emerging algorithms, to fully unleash the power of these two factors combined and make it as efficient as possible. This concludes my talk. Thank you very much.